The sun looks calm from Earth, but right now a giant dark region in its atmosphere is throwing charged particles into space. That flow may be heading toward Earth, carrying the power to shake our magnetic field and light up the polar skies. This is not science fiction. It is real space weather unfolding above the solar system. In this video, the story begins with that strange solar hole and ends with its possible impact on our planet. Please like, subscribe, and stay with the channel for more quiet journeys through real cosmic science. Earth moves around the sun at a distance that seems wide on a human scale and very small on the scale of the solar system. Around it, space does not remain empty in the simple way it appears in a night sky. It contains light, magnetic fields, and a thin flow of charged particles that spreads outward from the sun in all directions. A charged particle is an atom, or part of an atom that carries electric charge. This outward flow is called the solar wind. It is not wind in the sense of moving air. It is a stream of matter so thin that no breath or pressure could be felt by a person standing in it. Even so, it fills the space around Earth and reaches far beyond the orbit of the outer planets. From the ground, Earth seems wrapped by air and weather and cloud. Beyond that familiar envelope, it travels through a wider environment that has its own steady motion. The planet does not move through stillness. It moves inside a current that is always present, though its speed and density change from time to time. Most days, the solar wind remains invisible to ordinary sight. It carries particles mostly made of electrons and the nuclei of hydrogen, with a smaller share of helium and traces of heavier elements. These particles stream away from the sun because the outer solar atmosphere is so hot that some of its material escapes the sun's gravity and continues outward into space. At Earth's distance, this flow has already crossed many millions of kilometers. It arrives spread thinly across a wide volume, yet it remains fast. Typical speeds range from a few hundred to many hundreds of kilometers each second. The number of particles in a cubic centimeter of this space is often small, much lower than in even the thinnest air near Earth's surface. For that reason, interplanetary space stays close to vacuum by everyday standards. Still, the solar wind matters because it never entirely stops. It presses gently but continuously on anything that stands in its path. It also carries the sun's magnetic field outward with it, drawing that field into long spirals as the sun turns. Earth is not passive inside this flow. The planet has its own magnetic field, generated deep inside by motion in its liquid outer core. On the largest scale, this field extends far into space and forms a protective region around the planet. The region is not solid or fixed. It bends and shifts under the pressure of the solar wind. On the side facing the sun, the field is compressed. On the night side, it stretches into a long tail. This broad interaction gives Earth a place within the sun's influence that is active rather than still. The planet meets the solar wind every moment. The meeting shapes a moving boundary between material coming from the sun and the magnetic shield that rises from Earth. This meeting does not resemble a storm front in air or a wave striking ashore. It is quieter and thinner, but it is also more extensive. It takes place across distances larger than Earth itself. The incoming flow slows, diverts, and transfers energy through magnetic forces and through collisions so rare that the term collision begins to lose its ordinary meaning. In much of this space, particles affect one another mainly through electric and magnetic fields rather than by direct impact. The result is a region of continual adjustment. Earth passes through it as part of its ordinary orbit, while the sun continues to send fresh material outward. The sky gives only indirect signs of this relation. Sunlight itself is the clearest sign, warming the planet and driving the climate and the circulation of air and water. Yet the solar wind belongs to a different aspect of the same star. It is not the bright beam that defines day. It is a thin plasma, a state of matter in which atoms have been separated into charged parts. Plasma responds strongly to magnetic fields, and for that reason the space between Sun and Earth behaves differently from ordinary gas in a room or cloud in the lower atmosphere. Invisible lines of magnetic force guide motion, store energy, and sometimes release it. Earth, suspended inside this plasma flow, remains connected to the Sun in a way that is physical and continuous. Spacecraft provide much of what is known about this environment. Instruments placed above Earth's air measure particle speed, particle density, temperature, and magnetic direction. They show that conditions in near-Earth space change over hours and days. Some intervals are relatively quiet, some bring stronger pressure, faster flow, or sharper changes in magnetic structure. Observations indicate that these changes can affect the region around Earth in measurable ways. Radio signals can alter. Satellites can experience drag changes in the upper atmosphere, and bright auroral light can appear in high-latitude skies. The broad setting, even at this outermost level, is already one of connection. Earth is a world with oceans, rock, air, and life. Yet it also remains a small magnetized body moving through a stream from its star. This setting gives scale to the topic. The Sun does not influence Earth only through warmth and daylight. It also extends itself outward through matter and magnetism. This solar wind forms the most persistent part of that outward reach. It is present during quiet solar conditions and during more disturbed intervals as well. The difference lies in how fast it flows, how dense it becomes, and how its magnetic field is arranged when it reaches Earth. In some periods the interaction remains modest. In others it grows stronger and more complex. Measurements show that the timing of these changes matters, because Earth rotates beneath them while continuing its yearly path around the Sun. The outer environment therefore has structure, even when it looks empty. Earth moves within a broad domain shaped by the Sun and bathed in solar material that has travelled across space. The effect is subtle at human scale and immense at planetary scale. It belongs neither to weather nor to ordinary vacuum, but to a middle condition that space science has slowly learned to describe through observation. In that condition, the Sun is never absent. Its influence continues past the visible light of day and reaches the planet as a flowing extension of its outer atmosphere. Earth receives that flow constantly, responds to it through its magnetic field, and carries on within it as one small world inside a larger solar medium. The solar wind does not simply drift away and disappear near the planets. It continues outward and shapes a vast surrounding region that encloses the known planets and many smaller bodies. This region is called the heliosphere. The word refers to the sphere of the Sun, though the true shape is not a perfect sphere. It is a broad bubble in space formed by the continuous outward pressure of solar material against the much thinner gas that exists between the stars. That interstellar gas is the matter spread through the Milky Way outside the direct flow from any one star. The heliosphere marks the reach of the Sun as a physical presence. It is not only a source of light seen from afar, it is also a star that extends its atmosphere outward across enormous distance. Near the Sun, the solar wind expands freely. Farther out, it still moves fast, though it gradually changes as it travels. It crosses the orbit of Mercury, then Venus, then Earth, and continues beyond Mars. It passes the region of the giant planets and reaches still farther into the dark, where sunlight grows weak and the sun becomes only one bright star among many. Even there, the solar wind remains present. It carries the sun's magnetic field and pushes against the surrounding interstellar medium. The boundary between the solar domain and the broader galactic environment lies very far away, at distances far beyond the major planets. Spacecraft launched in the 20th century have taken decades to approach and cross these outer limits, turning an abstract scientific picture into something directly measured. Within this vast region, the solar wind is the main shaping force. It creates a cavity in the interstellar gas and keeps that cavity inflated. The pressure involved is not like the pressure inside a balloon held in the hand. It is far weaker, spread over immense distance, and maintained by a constant stream rather than by sealed walls. Even so, the effect is real. The heliosphere exists because the sun never stops releasing matter from its hot outer atmosphere. This release changes with solar activity, but the long outward motion remains. The whole system of planets travels inside that moving envelope. The shape of the heliosphere depends on more than the sun alone. The solar system moves through the local interstellar medium, and that motion affects the form of the outer boundary. Observations and models indicate that the heliosphere is broader in some directions and more drawn out in others. It is shaped by the balance between outward solar pressure, inward pressure from interstellar gas, and magnetic forces on both sides. It also changes over time as the solar cycle rises and falls. The solar cycle is the long pattern of changing magnetic activity on the sun, lasting about 11 years from one period of high sunspot number to the next. During more active periods, the properties of the solar wind and the magnetic field it carries become more varied, and the outer solar bubble responds. The outer edge of the heliosphere is not a sharp shell like the skin of fruit. It is a set of transition regions. One important boundary is where the solar wind slows from faster than the local speed of waves in the plasma to slower than that speed. This region is called the termination shock. A shock in space is a zone where conditions change quickly, including speed, density, and temperature. Farther out lies the heliopause, the boundary where the outward flow from the sun is balanced by the pressure of the interstellar medium. Beyond that, the material and magnetic field belong mainly to interstellar space, rather than to the sun's direct outflow. These regions are difficult to picture because they are so large and so thin, but their existence has been confirmed by long-travelling spacecraft and by careful interpretation of their data. Closer to the sun, inside the planetary region, the heliosphere provides the true large setting for space weather. Space weather refers to changing conditions in space that affect planets, spacecraft, and technological systems. It includes shifts in the solar wind, magnetic disturbances, and bursts of energetic particles. These changes do not occur in isolation near Earth. They arise within the wider solar domain and travel through it. Earth is one point inside a much larger structure. The same broad outflow that brushes past Earth also sweeps around the orbits of other planets, though each world responds in its own way depending on whether it has an atmosphere, a magnetic field, or neither. The heliosphere also affects the passage of cosmic rays, which are very energetic particles arriving from beyond the solar system. The outward magnetic field of the sun and the solar wind together reduce the number of some of these particles that reach the inner planets. This shielding is not complete, and it changes with solar activity. When the sun is more active, the structure of the heliosphere tends to block a larger share of lower-energy galactic cosmic rays from entering the inner solar system. In that sense, the sun does not only send material outward, it also modifies what comes inward from the galaxy. The solar system lives inside a filtered region, one shaped by its star in both directions. Seen at the wider scale, the Sun becomes less like a distant glowing object and more like the center of a physical system with flowing boundaries. The planets orbit inside light, heat, magnetic structure, and moving plasma. The heliosphere is the largest continuous expression of that system. It extends the Sun's influence far beyond what sunlight alone might suggest. It also shows that the path from the Sun to Earth is not short in concept, even if it is direct in geometry. Earth is embedded in a layered solar environment whose outermost form reaches into interstellar space. This broad picture remains important because it sets the scale of all smaller solar effects. Any changing region near the Sun, any stream of fast particles, and any magnetic disturbance that later matters near Earth begins as part of this greater flowing bubble. The heliosphere is therefore not a distant side note. It is the true outer body of the Sun's domain. Within it, the planets move as travelers inside an extended atmosphere that has no firm wall near them and no silence in the strict sense. There is only varying thinness, steady outward motion, and a persistent connection to the star at the center. Within the Milky Way, the Sun occupies no grand central position. It moves through one ordinary part of a barred spiral galaxy, circling the galactic center at a distance of many thousands of light years. A light year is the distance light travels in 1 year. On galactic scales, this places the Sun in a broad outer district, rather than in the dense and bright inner regions. Around it lies the local interstellar neighborhood, a sparse region of gas, dust, magnetic fields, and nearby stars. This setting gives the Sun perspective. It is one star among many billions in the galaxy, neither the largest nor the smallest, neither unusually young nor especially old. Its importance belongs not to rarity, but to nearness. Because Earth travels around it, even ordinary processes on the Sun become immediate and physically meaningful. From a distance, the Sun would appear as a yellow-white point of light, modest in size compared with giant stars and stronger in mass and brightness than many red dwarfs. It belongs to the main sequence, the long stable stage during which a star shines by fusing hydrogen into helium in its core. Fusion is the process in which light atomic nuclei join together and release energy. The Sun has remained in this stage for billions of years, and is expected to stay in it for billions more. That long stability makes it a dependable source of energy for Earth, yet it does not mean the Sun is motionless or simple. A stable star can still show changing magnetic activity, surface structure, and outer atmospheric flow. Stability, in this case, means that the star does not collapse or swell violently over short spans of time. It does not mean that every layer behaves in the same way from day to day. The stars nearest the Sun help show its ordinary nature. Some are smaller and cooler, producing less light and burning their fuel more slowly. Some are larger and hotter, with shorter and more intense lives. The Sun sits between these extremes. Its surface temperature, mass, and brightness place it among the common categories of stars that populate the galaxy. Even so, the exact balance inside such a star produces a rich and layered behavior. Gravity pulls inward. Pressure from hot gas and radiation pushes outward. Deep nuclear energy supports the whole structure. Over immense spans of time, these forces remain in broad balance. The Sun therefore persists not because it is inactive, but because its inward and outward tendencies stay closely matched. The local region around the Sun contains thin interstellar gas and traces of dust. Not the dense clouds where stars are born in large numbers. The Sun is passing through this region as part of the shared motion of nearby stars. it carries its planets, smaller bodies, and heliosphere with it. This movement through the galaxy does not dominate life on Earth from one year to the next, yet it helps define the wider setting of the solar system. The Sun is not anchored in place. It is a moving star within a moving galaxy. Its magnetic outflow meets the interstellar medium because both are in motion, and the shape of the heliosphere reflects that meeting. Compared with more dramatic stars, the Sun can seem quiet. It does not explode as a supernova. It does not shed its outer layers in unstable pulses. It does not vary greatly in brightness on short timescales. Yet quiet is a relative term. Its surface and atmosphere still churn, twist, and release energy through magnetic change. The same star that appears calm from several light-years away can generate solar flares, coronal mass ejections, and coronal holes when viewed closely with modern instruments. These are not signs of a star leaving its stable life stage. They are part of how magnetized plasma behaves in the outer layers of an active but ordinary main sequence star. This balance between ordinary character and local importance defines the Sun's place among nearby stars. Many stars possess magnetic fields, many have winds of escaping material, many show spots or active regions on their surfaces. The Sun is scientifically valuable because it is near enough to study in detail. Features too small to resolve clearly on most other stars can be traced on the Sun across hours and days. Spacecraft can sample the outward flow that begins in its atmosphere. Telescopes can map motions and magnetic structure across its visible face. Through that nearness, the Sun becomes the standard example for stellar physics and the most direct laboratory for understanding how a magnetically active star affects surrounding worlds. Its age also matters. The Sun forms roughly 4.5 billion years ago from a cloud of gas and dust that collapses under gravity. Most of the material gathers at the centre, where pressure and temperature rise until fusion begins. The remaining material spreads into a disk from which planets, moons, asteroids, and comets eventually form. The Sun therefore does not merely illuminate the solar system. It is the main surviving mass from the same original cloud that gives rise to Earth and the other planets. This shared origin ties the star and its worlds into one history. It also means that the Sun's present behaviour unfolds in a mature planetary system that has already undergone long evolution. In the local galactic neighbourhood, the Sun stands as a normal star that happens to have one special consequence. A planet with air, water, rock, and life circles it at a distance where its energy allows liquid water to persist at the surface. That fact makes changes in the Sun more than an astronomical curiosity. Variations in solar radiation at Earth are usually small across the solar cycle, but changes in magnetic activity and particle outflow can strongly affect near-Earth space. This is the scale shift that matters, a process that remains modest compared with the full violence possible in the universe can still alter satellite operations, radio transmission, and auroral light over a living planet. So the Sun, viewed among its neighbouring stars, appears both ordinary and singular. It is ordinary in class, life stage, and galactic placement. It is singular only because Earth belongs to it. Within the wider field of stars, it gives no sign of being an extreme object. Yet its nearness allows the details of stellar activity to become part of daily human concern. The broad galactic setting narrows here to one central truth. An ordinary star is fully capable of shaping the environment of its planets through light, heat, magnetism, and flowing plasma, and that shaping begins long before attention settles on any one feature upon its surface. From the distance of Earth, the Sun appears as a brilliant disk, steady in shape and almost featureless to the unaided eye. Its light is too strong for direct viewing without protection, and that brightness hides much of the structure that instruments later reveal. Yet the visible face of the Sun, once carefully observed through proper filters and telescopes, is not a solid shell, and not a simple surface in the ordinary sense. It is the photosphere, the layer from which most visible sunlight escapes into space. The word means sphere of light. It is called the solar surface because it is the depth at which the Sun becomes opaque enough that light can no longer move outward freely from below. Light from deeper layers is scattered and absorbed many times before it reaches this level. At the photosphere, the escaping radiation finally begins the final part of its journey outward. This visible layer is thin compared with the Sun's full size. The Sun has a radius of about 700,000 kilometers, while the photosphere is only a shallow skin within that enormous sphere. Even so, it defines the edge that human eyes and ordinary cameras most readily perceive. It is not hard like rock, not liquid like an ocean, and not gas in the familiar sense of the air near Earth's surface. It is plasma, hot enough that atoms are partly broken into charged particles. Even in this visible layer, matter behaves under the combined influence of gravity, heat, radiation, and magnetic fields. The result is a bright, restless boundary where energy from deep inside the Sun emerges into open space. The temperature of the photosphere averages around 5,500 degrees Celsius. At that temperature, it shines strongly in visible light, which is why the Sun appears white in space and often yellowish when seen through Earth's atmosphere. The color shift from white to yellow or red near sunrise and sunset comes mainly from scattering in the atmosphere, not from a change in the Sun itself. In careful space-based images, the photosphere is closer to white, with subtle variations depending on instrument design and wavelength. This brightness is the outward sign of energy that has taken a very long path from the core, where fusion releases it, through dense inner layers, where it moves slowly outward by radiation and by motion of hot material. At the edge of the solar disk, the photosphere appears slightly dimmer than at the center. This effect is called limb darkening. It happens because the line of sight near the edge passes through higher, cooler layers of the photosphere, while the view toward the center reaches somewhat deeper, hotter layers. This simple visual change reveals something important about the Sun. The visible disk is not a flat glowing plate. It has depth, and the temperature changes across that depth. Even a basic telescopic observation begins to show that the Sun is layered. The disk presents a face, but it is the face of a star whose outer visible region is only a thin boundary over a much larger interior. The photosphere also rotates with the Sun, though not all parts rotate at the same rate. The Sun is made of plasma rather than rigid solid material, so its equatorial regions rotate faster than regions nearer the poles. This pattern is called differential rotation. At the equator, one full turn takes about 25 days as measured relative to distant stars, while higher latitudes take longer. This difference matters because it stretches and twists the Sun's magnetic field over time. At the level of the visible disk, the effect can be followed through the motion of surface features across days and weeks. The Sun, even where it appears calm, is already revealing internal motion through the changing placement of marks and patterns on its face. In ordinary white light observation, the photosphere is the primary source of the Sun's visible output. Most of the energy reaching Earth as sunlight comes from this layer. It defines the disk seen during daytime and the sharp dark circle blocked during an eclipse. During a total solar eclipse, when the moon covers the photosphere, the sudden drop in visible brightness reveals much fainter layers above it. That dramatic contrast teaches a simple lesson. The visible surface dominates the sun's ordinary appearance because it is vastly brighter than the outer atmosphere beyond it. Without that overwhelming light, the sun would look very different. With it, the photosphere remains the main face presented to the inner solar system. Although the photosphere seems smooth from a casual view, precise observation shows constant fine structure. Small bright and dark variations cover it, shaped by rising and sinking motions of hot plasma. These patterns belong to the visible layer itself and show that the sun's surface is active on small scales even in the absence of larger dark spots. The photosphere is therefore not merely a screen through which deeper energy passes. It is a dynamic region where that energy meets changing material conditions before escaping as light. It is also where magnetic fields become visible through their effects on brightness and structure. The term surface must be used carefully here. A person could not stand on it, and a spacecraft could not land on it as on a planet or moon. The density is too low, the temperature too high, and the material too fluid in behavior. Yet the photosphere still acts as a practical surface for observation, because it marks the transition between the sun's opaque body and the more transparent layers above. In that sense, it is a visible boundary, not a solid one. It is the level at which the sun stops hiding its light and begins to cast it clearly into space. Seen in this way, the solar disk becomes more than a bright circle overhead. It is the top of a deep luminous body, the place where internal energy first becomes visible in direct form. The photosphere carries the appearance of steadiness, but its brightness, rotation, and subtle changes already show that the sun is a star in motion. Every beam of ordinary sunlight that falls on Earth leaves from this visible layer the familiar warmth of day, the sharp shadows of noon, and the white brilliance seen above clouds all trace back to this thin radiant shell. The photosphere is therefore both common and profound common, because it is what every day reveals, and profound because it is the outer, visible expression of a star whose deeper workings remain hidden beneath it. Across the visible solar disk, the photosphere does not remain smooth when seen with fine enough detail. It shows a shifting pattern of bright cells bordered by darker lanes, a texture so widespread that it covers nearly the whole surface outside the larger dark regions. This pattern is called granulation. A granule is a small, short-lived cell of rising hot plasma. Plasma is matter in which atoms have partly separated into charged particles in the photosphere. This material moves because heat from below is still working its way outward. The movement belongs to convection, the transport of energy by the motion of hot material rising and cooler material sinking. In a pot of heated water, convection creates rolling motion. In the sun, the same general process takes place in plasma rather than liquid water, under gravity far stronger than Earth's, and at temperatures beyond ordinary experience. The bright centers of granules mark places where hotter material rises from below and reaches the visible layer. As it arrives, it radiates energy into space and begins to cool. The darker boundaries between granules are where cooler material sinks back down. The brightness difference is modest, but with suitable instruments it becomes clear and regular. Each granule spans roughly 1,000 kilometers, though sizes vary, and each one lives for only a brief time before changing shape, fading, dividing, or merging with others nearby. The photosphere is therefore patterned not by permanent structure, but by countless small overturning motions that appear and vanish continuously. The visible solar surface resembles a field of luminous cells in slow transformation, each one carrying part of the sun's internal heat toward open space. This pattern reveals an important physical truth. Light leaving the sun does not emerge from a silent fixed shell. It rises through a layer fed from below by moving material. In deeper regions of the sun, energy travels outward largely by radiation through dense matter. Higher up, in the outer part of the interior, convection becomes the more effective way to transport energy. Hot plasma rises because it is less dense than the cooler plasma above it. As it reaches lower pressure regions near the photosphere, it expands, cools, and eventually sinks again. The surface pattern of granules is the visible top of this deeper convective zone. It is a surface sign of a much larger circulation that reaches far beneath the photosphere. The sizes and lifetimes of granules matter because they show how rapidly the sun renews its visible texture. A human face or a rocky landscape can keep the same small details for years. The photosphere does not, even without sunspots, flares, or dramatic eruptions. It changes minute by minute. A given bright cell grows and dissolves. A dark lane shifts position. New cells emerge while old ones vanish. The whole disk outside larger magnetic features is alive with this modest but ceaseless motion. The process is not violent in appearance when viewed at ordinary speed, yet it is energetic in physical terms. It represents the steady release of the sun's internal energy at the level where that energy finally escapes into space as light. Above the scale of granules lies a broader pattern called supergranulation. These cells are much larger and last longer, spanning tens of thousands of kilometers and surviving for about a day or more. They are not seen in the same direct bright cell way as ordinary granulation, but they can be traced through motions across the surface and through the gathering of magnetic elements at their boundaries. Supergranulation suggests that convection on the sun works on several scales at once. Small rising and sinking motions are nested within broader flows, and those broader flows help organize weak magnetic fields near the surface. The photosphere is therefore not only a radiant boundary, it is also a moving landscape of layered circulation. The brightness of the photosphere depends on temperature, and convection helps maintain that brightness by bringing up hot material from below. The surface thus acts as an interface between interior heat transport and outward radiation. This balance shapes the familiar sunlight received at Earth. The average brightness of the sun changes only slightly over the solar cycle, but local variations across the surface can be more noticeable. Some places appear a little brighter because hotter plasma is exposed there. Some places appear darker because magnetic fields suppress convection and reduce the upward transport of heat. The ordinary granular pattern belongs to the first case, where convection proceeds relatively freely and supplies fresh hot plasma to the visible layer. At high resolution, the edges of granules are not perfectly regular. They curve, split, and narrow into dark channels where cooler plasma descends. The whole field resembles a moving mosaic, though no fixed tiles exist. This imagery helps only to a point, because the sun's surface is not made of separate pieces. It is a continuous fluid medium, with brightness shaped by temperature and motion. The mottled appearance is a pattern of process rather than a pattern of objects. What looks like a textured skin is actually a visible signature of thermal motion in plasma under strong gravity and intense radiation. This constant overturning also contributes to the way magnetic fields behave at the surface. Weak fields can be swept into the darker lanes between granules, where flows converge. Over time, these fields may collect, fragment, or reconnect in changing arrangements. The details belong to magnetohydrodynamics, the study of electrically conducting fluids and magnetic fields acting together. In plain terms, the sun's plasma moves the magnetic field, and the magnetic field can then alter how the plasma moves. Even where no large active region is present, this mutual influence is already underway on small scales across the photosphere. The surface pattern of heat flow becomes, at the same time, part of the pattern of magnetic organization. The photosphere's granular texture therefore serves as more than visual detail. It shows that the sun's outward light is linked to movement from below. Each bright cell is a temporary window onto rising heat. Each dark lane marks a return flow downward. Together they form the most common state of the visible solar surface, on calm days of observation, when no dramatic dark spot draws the eye. Granulation remains the true fabric of the sun's face. It is modest in contrast, fine in scale, and endlessly renewed. It makes the visible disk less like a polished lamp and more like a living thermal surface in continuous circulation. Sunlight reaching Earth appears steady because the immense number of these cells averages into an almost unchanging brilliance across the whole disk. Yet this steadiness is built from movement, the warmth felt on skin, the illumination of cloud and sea, and the ordinary certainty of day all emerge from a star whose visible surface is constantly turning over at small scale. The calm appearance of the sun from far away rests on countless small rising and sinking motions close to the photosphere. In that sense, the sun's light is not only radiant, it is also convective in origin at the last visible stage, carried upward by the slow, persistent labour of hot plasma reaching the surface and cooling beneath the open sky of space. Across the photosphere, the granular pattern often continues without interruption, but at certain times darker features appear that stand out clearly against the surrounding brightness. These features are called sunspots. A sunspot is a region on the visible solar surface where the temperature is lower than its surroundings, making it appear dark by contrast. The difference in temperature is not extreme in absolute terms, even within a sunspot. Temperatures remain in the range of several thousand degrees Celsius. The darkness arises because the surrounding photosphere is hotter and therefore brighter. Against that bright background, the cooler region appears as a distinct mark. A typical sunspot has a central dark core known as the umbra, surrounded by a lighter, more textured region called the penumbra. The umbra shows the lowest temperature within the spot, while the penumbra contains streaked structures that reflect more complex flow and magnetic arrangement. These structures resemble fine filaments radiating outward from the center, giving the penumbra a subtle pattern when seen with sufficient detail. The full size of a sunspot can vary widely. Some are smaller than Earth, while others extend across areas several times larger than the planet. They can persist for days or even weeks, gradually changing shape, growing, or fading as the solar surface evolves. The presence of a sunspot signals a concentration of magnetic field. The sun's magnetic field is not uniform. It emerges from the interior, rises through the convective zone, and becomes visible at the photosphere where it affects the motion of plasma in a sunspot. The magnetic field is strong enough to suppress convection. When convection is reduced, less hot material rises from below, and the surface cools slightly relative to its surroundings. This reduced heat flow explains the darker appearance. The magnetic field does not simply sit still within the plasma. It channels and constrains motion, guiding charged particles along its lines, and limiting the usual rising and sinking flows seen in the granular pattern. Sunspots often appear in groups rather than as isolated features. These groups can include several spots of different sizes, sometimes arranged in pairs or clusters, with a leading and following structure as the sun rotates. The arrangement reflects the underlying magnetic configuration. Magnetic field lines rise from below the surface, loop outward into the solar atmosphere, and return to the surface at another point. The two ends of such a loop can appear as a pair of sunspots with opposite magnetic polarity. Polarity refers to the direction of the magnetic field. One spot may have field lines emerging outward, while the other has field lines entering inward. This paired structure reveals that sunspots are not separate objects but parts of a connected magnetic system. The number and distribution of sunspots change over time in a pattern known as the solar cycle. Over roughly 11 years, the Sun moves from a period of few visible spots to a period of many, then back again. During the more active phase, sunspots can appear at various latitudes across the solar surface, gradually shifting closer to the equator as the cycle progresses. Observations over centuries have shown that this cycle repeats with some variation in strength and timing. It reflects a deeper magnetic rhythm within the Sun, driven by the combined effects of rotation, convection, and the movement of plasma in its interior. The photosphere becomes the stage where this internal magnetic activity is made visible. Around sunspots, additional features often form. Bright regions known as faculae can appear, especially near the solar limb where they become more visible due to viewing angle. These regions are slightly hotter and associated with magnetic concentrations that enhance brightness rather than suppress it. The coexistence of darker and brighter areas illustrates that magnetic fields can influence the surface in different ways, depending on their structure and strength. In some places, they block convective heat flow and create dark spots. In others, they allow or even enhance localized heating, producing brighter patches. Sunspots are not static marks. They evolve as the magnetic field beneath them changes. A spot may grow as more magnetic flux emerges from below, then break apart into smaller fragments as the field disperses. The penumbra can expand or contract, and the umbra can shift in shape. Over time, the magnetic field may weaken, allowing convection to resume and the region to brighten again until it blends back into the surrounding photosphere. This life cycle reflects the dynamic balance between magnetic forces and plasma motion. Neither dominates permanently. Instead, they interact continuously, shaping the visible appearance of the Sun. The presence of strong magnetic fields in sunspot regions also links the photosphere to higher layers of the solar atmosphere. Magnetic field lines extend upward from the surface into the chromosphere and corona. These lines can store energy when they're twisted or stretched by motion at the surface. Although that stored energy becomes more evident in higher regions, its origin often lies in the rearrangement of magnetic fields rooted in the photosphere. Sunspots, therefore, are more than surface markings. They are anchors of larger magnetic structures that reach far above the visible disk. In careful observation, the distribution of sunspots across the solar surface reveals patterns that repeat over many cycles. The average latitude of spots, their grouping, and their magnetic orientation all follow systematic trends. These patterns help scientists understand how the Sun's magnetic field is generated and how it reverses direction over time. At the end of each solar cycle, the overall magnetic polarity of the Sun flips, so that the next cycle begins with opposite orientation. This long-term change occurs without altering the Sun's general brightness or structure, but it affects how magnetic features appear and evolve on the surface. Despite their darker appearance, sunspots do not reduce the Sun's total energy output in a simple way. The darker regions are often balanced by brighter faculae nearby, and the overall variation in solar brightness across the cycle remains small. However, the presence of sunspots signals periods when magnetic activity is higher, and that activity can lead to changes in the outer atmosphere and the solar wind. The photosphere, through its spots and bright regions, provides the first clear visual evidence of these changes. Thus, the the calm granular surface described earlier gives way, at times, to a more structured appearance shaped by magnetism. Dark cores and lighter penumbral patterns interrupt the uniform brightness. Groups of spots trace out invisible magnetic loops. The sun's visible face becomes a record of deeper processes, where convection and rotation work together with magnetic fields to produce features that persist long enough to be followed across days. The photosphere remains the same thin, radiant boundary, but in these regions it reveals a more complex character, one in which energy flow and magnetic structure combine to shape the appearance of the star's surface. Above the photosphere lies a region that cannot usually be seen in ordinary daylight because the visible surface is so bright. When that brightness is reduced by special instruments, or briefly hidden during a total solar eclipse, the sun reveals a faint outer atmosphere extending far into space. This region is the corona. The word means crown, a fitting description for the pale, luminous halo that surrounds the darkened solar disk during an eclipse. The corona is not a dense envelope like the lower atmosphere of a planet. It is extremely thin, made of plasma spread across vast distances, yet it reaches far beyond the visible surface and forms the outer atmospheric domain from which the solar wind begins to flow. The most striking property of the corona is its temperature. Although it lies farther from the sun's main energy source than the photosphere, it is much hotter, reaching temperatures of millions of degrees Celsius in many regions. This seems contrary to ordinary experience, where distance from a hot object usually means lower temperature. In the sun's atmosphere, however, temperature does not simply decrease with height. The visible surface is cooler than the thin outer atmosphere above it. Observations clearly show this, though the full details of coronal heating remain an active area of research. What is known is that magnetic fields play the central role. Motions at and below the photosphere shift the magnetic footpoints anchored in the surface. Energy is then carried upward and released in the corona through processes involving magnetic waves, small-scale reconnection, and other forms of magnetic stress and relaxation. Observations indicate that these mechanisms contribute to heating, though the exact balance among them remains uncertain. The corona is structured by magnetism. Plasma at coronal temperatures is strongly guided by magnetic field lines, so the corona does not spread evenly in all directions. Instead, it forms loops, streamers, plumes, and more diffuse regions whose shapes reflect the invisible magnetic skeleton beneath them. In images taken in ultraviolet and X-ray wavelengths, bright curved loops often arch above active regions. These loops mark places where hot plasma is trapped along closed magnetic field lines, meaning the field rises from the surface and returns to it nearby. Other regions appear more extended and less confined, suggesting field lines that open outward into space. The corona is therefore not simply a hot glow, it is a magnetic atmosphere whose form changes as the sun's field changes. Because the corona is so thin, its light is faint compared with the brilliance of the photosphere. Under normal conditions, scattered light in Earth's atmosphere overwhelms it. Coronagraphs, instruments that block the bright solar disk, allow scientists to observe the corona even without an eclipse. Spacecraft provide especially clear views because they avoid the distorting and scattering effects of air. These observations reveal that the corona is always present, though its shape changes over the solar cycle. During quieter phases, it tends to show a more organized appearance, with large streamers near the equator and darker open regions nearer the poles. During more active phases, the structure becomes more complex, reflecting the greater number of magnetic regions on the sun. The corona does not have a sharp outer edge. It thins gradually with distance, extending outward until it blends into the solar wind. Near the sun, It remains bound in part by gravity and magnetic structure. Farther out, the hot plasma expands and escapes. In that sense, the corona is both atmosphere and source region. It is the outer solar layer still visibly tied to the Sun, and it is also the beginning of a continuous outward flow that fills interplanetary space. Its material is sparse by ordinary standards, but the scale is immense. A thin atmosphere spread over millions of kilometers can still shape the whole inner solar system. The composition of the corona reflects that of the Sun more generally, with hydrogen and helium dominant and smaller amounts of heavier elements present in ionized form. Ionized means that electrons have been stripped away by high temperature. In this state, atoms emit and absorb light at specific wavelengths, allowing scientists to determine temperature, density, and motion. Much of what is known about the corona comes from this diagnostic light, spectroscopy. The study of light separated into its component wavelengths reveals highly ionized atoms that can exist only at very high temperatures. Such evidence established long ago that the corona is far hotter than the visible surface, even before the full mechanisms of heating were understood. The corona also changes on many timescales. Some loops remain for hours or days, some brighten or fade more quickly. Large-scale structures can persist through a rotation of the Sun and reappear when carried back into view. Smaller events flicker across it in abundance. This changing behavior reflects a restless balance between plasma and field. Material flows along loops, drains downward, or is heated in place. Magnetic connections shift as the surface below rotates and convects. Even where the corona appears quiet, it is not still in the strict sense. It is a continuously evolving atmosphere, shaped by forces that are partly visible and partly inferred from the behavior of light and plasma. Despite its heat, the corona would not feel hot in any ordinary sense if a person could somehow pass through a region of it. Temperature in plasma describes the energy of particles, but the density is so low that very little total heat would be transferred by contact. This difference between temperature and felt heat is important. The corona is an example of matter that is extremely hot and extremely tenuous at the same time. Its particles move with high energy, yet they are separated by such great distances that the plasma remains remarkably thin. The combination makes the corona physically unusual compared with everyday environments on Earth. In the wider outward to inward path of understanding, the corona stands as the first clear atmospheric layer above the Sun's visible face. It is no longer the bright photospheric surface from which ordinary sunlight escapes, yet it remains closely tied to that surface through magnetism. It shows that the Sun's atmosphere does not fade gently upward as a simple warm haze. Instead, it opens into a realm of unexpectedly high temperature, sparse matter, and large magnetic form, the quiet corona. Before attention settles on any darker openings within it, appears as a broad outer crown of hot plasma shaped into luminous patterns by invisible fields. It surrounds the Sun not as decoration, but as a real physical layer whose structure determines how solar material is held, heated, and in some places released into space. Within the corona, some regions appear darker than the surroundings when viewed in ultraviolet and X-ray light. These areas are called coronal holes. The name can mislead if taken too literally. A coronal hole is not a gap torn through the Sun, and not an opening into emptiness below. It is a region where the corona is cooler and less dense than nearby areas, so it emits less of the high-energy light that instruments detect. Against the brighter surrounding corona, it appears as a broad dark patch, invisible light. The Sun's bright photosphere still dominates ordinary appearance, and the whole cannot be seen in the simple way a sunspot can. Its darkness belongs mainly to special wavelengths that reveal the hot outer atmosphere. A coronal hole is best understood as a magnetic region. In many parts of the corona, magnetic field lines rise from the surface and bend back down nearby, forming closed loops. These loops can trap hot plasma and help keep the corona bright. In a coronal hole, by contrast, much of the magnetic field is open. Open field lines are lines that extend outward into space rather than returning quickly to the surface near their starting point. Plasma can flow outward along these paths more readily, and because less hot material remains confined there, the region tends to be less dense and less bright in coronal images. The darkness, therefore, reflects the geometry of the magnetic field and the resulting lower concentration of hot plasma. Coronal holes can form near the poles of the Sun and also at lower latitudes, near solar minimum. When the cycle is in a quieter phase, large persistent holes often occupy polar regions. These polar holes can last for many months. During more active phases of the cycle, the corona becomes more complex and holes can appear at different latitudes, sometimes as irregular regions extending toward the equator. When a lower latitude coronal hole rotates into a position facing Earth, it can become especially important for near-Earth space because the fast solar wind flowing from it may later reach Earth's magnetic environment. The size of a coronal hole can be enormous. Some span a substantial fraction of the solar disk in images, covering areas much larger than Earth. This large scale explains why reports sometimes describe a massive hole on the Sun. The phrase captures visual extent, but the underlying feature remains a difference in coronal structure rather than a cavity in the star itself. The Sun's visible surface remains present beneath the region, continuing to radiate ordinary sunlight. What changes above it is the state of the outer atmosphere and the magnetic arrangement that shapes that atmosphere. In that sense, a coronal hole is less like a crater and more like a district of altered atmospheric conditions. These regions are identified through remote sensing. Spacecraft that observe the Sun in ultraviolet wavelengths can detect the reduced emission clearly. The darkness is relative, not absolute. The coronal hole still contains hot plasma, but it contains less of it, and often at different temperature conditions than adjacent bright regions. Measurements also show characteristic magnetic patterns associated with these holes, magnetograms, which map magnetic field at the solar surface, often reveal that a coronal hole is dominated by one magnetic polarity over a broad area. This dominance supports the picture of field lines opening outward into the heliosphere rather than closing locally in balanced loops. The boundary of a coronal hole is rarely simple. It may curve, branch, narrow, or widen over time as solar rotation and magnetic evolution reshape the corona. Along the boundary, open and closed magnetic field regions meet, and this transition can be complex. Bright loops may line the edge, while darker interior regions stretch away toward higher latitudes or across part of the disk. As the Sun rotates, the apparent shape changes from Earth's viewpoint, and repeated observations over days reveal that the feature has both persistence and gradual evolution. Some holes last for several rotations of the Sun, returning into view again after moving around the far side. Others change more quickly or dissolve as the magnetic field rearranges. Although coronal holes are often discussed in relation to space weather, the feature itself belongs first to the corona as an atmospheric region. It must be understood on its own terms before any later effects are considered. The plasma inside the hole is less confined than plasma in nearby bright loop systems. The magnetic field is arranged in a way that offers outward pathways rather than closed traps. Density is lower, brightness is lower in specific wavelengths, and the region becomes a recognizable part of the Sun's outer atmospheric map. This is the direct physical meaning of the dark area. It is not a wound, not a void, and not an absence of the sun. It is a coronal state created by magnetic openness. The relation between coronal holes and other solar features is sometimes close but not identical. A hole may lie away from the brightest active regions, or it may extend near them. It may overlap with quiet-looking parts of the disk in visible light. The underlying photosphere does not necessarily show dramatic dark marks where the coronal hole appears above. This difference reminds observation that the sun looks unlike itself in different wavelengths, in white light. The visible surface presents one pattern. In ultraviolet light, the hot outer atmosphere presents another. Coronal holes belong to that second view. They are atmospheric features revealed by the light of ionized plasma at high temperature. Scientists continue to study how exactly these holes form, persist, and decay as the sun's magnetic field evolves. Observations indicate that large-scale magnetic organization and the opening of field lines are essential. It remains uncertain in detail how local magnetic processes combine to create the full, long-lived shape of every hole, especially during more complex phases of the solar cycle. Even so, the broad picture is well established. Coronal holes are regions of open magnetic field. Reduced coronal density and diminished emission in ultraviolet and X-ray light. They are stable enough to be tracked, large enough to matter across the solar system, and common enough to be part of the sun's normal outer behavior. In the outward atmosphere of the sun, then, the quiet corona does not remain uniform. It contains bright arches, diffuse glow, and also these darker territories where the magnetic field opens toward interplanetary space. A coronal hole is one such territory. It occupies the sun's outer atmosphere rather than its visible surface, and it signals that the corona there is arranged for escape rather than confinement. Its darkness is a physical clue, a map of lower density and open magnetic connection. Seen in this way, the so-called hole becomes less a dramatic rupture and more a broad atmospheric gateway shaped by the sun's magnetism. From within a coronal hole, plasma flows outward more readily than it does from many other parts of the corona. This outward movement becomes the fast solar wind. The term fast does not mean explosive in the everyday sense. It refers to a stream that reaches higher speeds than the slower background flow that often fills interplanetary space. Measurements from spacecraft show that solar wind emerging from coronal holes commonly travels at several hundred kilometers each second, and can rise to around 700 or 800 kilometers each second. The exact speed depends on the structure of the source region, and on conditions during the outward expansion. What matters first is the physical setting at the sun. In a coronal hole, magnetic field lines open outward. The coronal plasma is less confined, and hot material gains a comparatively direct path into space. The solar wind begins in the corona, not at the visible surface. The photosphere remains the bright lower boundary of the sun's ordinary appearance, while the corona forms the hot outer atmosphere where particles can escape. In a coronal hole, the open magnetic geometry allows that escape to proceed more efficiently. The plasma there is still affected by gravity, collisions, waves, and electric and magnetic forces, but the overall result is a stronger outward acceleration than in many closed-loop regions. Scientists describe this as an outflow from open magnetic flux, meaning from magnetic field that extends into the heliosphere, rather than bending back promptly to the sun. The fast wind is therefore not only a matter of high temperature, it is also a matter of topology, the arrangement of the magnetic field. As this material leaves the sun, it expands into decreasing pressure. The density drops rapidly with height, and the particles continue outward across many millions of kilometers, the plasma remains very thin, but it carries momentum and magnetic structure with it. The sun's magnetic field, frozen into the moving plasma on large scales, is drawn outward and twisted into a spiral by solar rotation. This means that the stream leaving a coronal hole does not travel as a narrow straight beam in the simple sense. It expands and curves as part of the larger rotating outflow from the sun. A region that appears broad on the solar disk can therefore produce a large stream in interplanetary space, sweeping across wide angular extent as the sun turns. The fast solar wind differs from slower wind in more than speed. Its temperature history, density, and particle composition can also differ in systematic ways. In general, fast streams tend to be less dense and less variable on short timescales than slow wind, though the full picture is complex. The slow solar wind often arises from regions where the magnetic structure is more tangled or where plasma release is more intermittent. By contrast, the open magnetic environment of a coronal hole produces a flow that is often more steady once established. Observations indicate that the fast wind also carries characteristic signatures in the charge states of ions and in the abundance of certain elements, allowing researchers to connect measured wind near spacecraft back to conditions in the source region on the Sun. One reason for the higher speed remains an area of active study. Though the broad framework is well supported, magnetic waves, especially Alpha-Venn waves, appear to play an important part. An Alpha-Venn wave is a disturbance that travels along magnetic field lines through plasma, carrying energy and momentum. Motions in and below the photosphere can shake magnetic field lines rooted in the surface, launching such waves upward into the corona. In open field regions, these waves may help accelerate the plasma outward by transferring momentum and by contributing to heating as they interact and dissipate. Observations support an important role for wave-driven processes in coronal holes, though the exact mix of mechanisms is still being refined. Magnetic geometry, wave activity, and thermal expansion all appear to contribute. The flow does not leave the sun at full mature form all at once. Near the lower corona, the wind is still being accelerated. As it moves farther outward, it reaches the higher speeds measured by spacecraft placed between the sun and Earth or beyond. During this journey, the stream can preserve memory of its source region. Large coronal holes often produce recurrent fast streams, meaning streams that return in a similar pattern each time the same hole rotates back into a position that directs the outflow toward the same part of space. This recurrence has long been an important clue in solar terrestrial physics. It shows that some source regions on the Sun persist long enough to influence conditions at Earth again and again across successive solar rotations. From the standpoint of the Sun, the fast wind is a natural extension of the coronal hole itself. The hole is not merely a darker region to be mapped. It is a source of moving plasma that leaves the solar atmosphere and enters the heliosphere. The darkness seen in ultraviolet images and the high-speed stream measured in space are two aspects of one physical structure. One belongs to remote sensing of the atmosphere near the Sun. The other belongs to direct sampling of the outward flow after it has travelled across space. Together they reveal continuity between solar atmosphere and interplanetary medium. The stream also carries embedded irregularities and waves. It is not perfectly smooth. Small fluctuations in magnetic field direction, density, and speed move with it. These variations can arise from processes near the Sun or from the evolution of the stream during travel. Even so, a mature fast stream often remains more coherent than the slower, more mixed wind around it. That coherence helps explain why coronal holes have been linked to relatively predictable, though not harmless, forms of space weather. The source region may not produce the most violent solar disturbances, but it can produce broad and persistent streams that matter greatly when they sweep across planetary environments. Near the Sun, however, the essential point is still local and atmospheric. The fast solar wind is the outward continuation of open coronal structure. It begins where plasma is less trapped, where magnetic lines guide material away from the Sun, and where energy deposited in the corona helps drive expansion into space. The process belongs to the Sun's normal behavior. Coronal holes are common features of the corona, and fast wind from them is a regular part of heliospheric circulation. There is no need for an eruption to create every strong stream. Sometimes the Sun simply presents an open region, and that openness is enough to launch a wide, swift outflow. In this way, the coronal hole becomes dynamic rather than merely descriptive. It is not only a dark area in an image, it is a source region with motion, carrying solar material beyond the corona into the surrounding solar system. The plasma that leaves it spreads, accelerates, and joins the larger spiral structure of the solar wind. Its speed sets it apart from slower background flow, and its origin in open magnetic fields explains why it can escape so readily. Within the outer atmosphere of the Sun, this is the direct consequence of magnetic openness, not emptiness, not silence, but a steady and powerful release of hot plasma into space. As the fast solar wind leaves the Sun and moves outward through interplanetary space, it does not travel in isolation. Ahead of it, slower solar wind may already occupy the path. This slower wind, having left the Sun earlier from different regions, moves at a reduced speed and forms a background through which the faster stream must pass. When a high-speed stream catches up with slower material, interaction begins. The faster flow cannot simply pass through without consequence. Instead, it compresses the plasma ahead of it, increasing density and magnetic field strength in that region. This interaction creates a structure known as a co-rotating interaction region. A co-rotating interaction region forms because the Sun rotates, carrying the source of the fast wind with it. As a coronal hole rotates across the solar surface, it continues to release fast solar wind over many days. This stream expands outward in a spiral pattern due to solar rotation. The slower wind ahead also follows a spiral path, but at a lower speed. Where these two streams meet, a compression zone develops. Plasma and magnetic field lines are pushed together, forming a region of enhanced pressure and altered magnetic structure. This region travels outward with the flow, maintaining its identity over large distances. The structure of such a region is not uniform. At its leading edge, where the fast wind first encounters slower material, compression increases, density rises, and magnetic field lines become more closely packed. Behind this compressed zone, the faster wind continues, while ahead of it the slower wind is gradually accelerated by the pressure from behind. The result is a broad transition between different flow speeds rather than a sharp boundary, over time and distance. This interaction can steepen into shock-like features, where changes in speed, density, and magnetic field become more abrupt. These shocks are not like sound waves in air, but are transitions in plasma, where conditions shift rapidly across a narrow region. Because the Sun rotates, the source of the fast wind continues to send out new material along a slightly shifted path. This creates a spiral pattern in space, sometimes called a Parker spiral, after the scientist who described the rotating solar wind structure. The interaction region follows this spiral geometry, extending across a wide sector of interplanetary space. As a result, Planets moving in their orbits can encounter these regions repeatedly if the coronal hole persists. Earth, orbiting the Sun once each year, may pass through the same pattern as it is renewed with each solar rotation of roughly 27 days. Within the interaction region, physical conditions differ from both the fast and slow wind around it. The compressed plasma has higher density and stronger magnetic field strength. The direction of the magnetic field may also change, sometimes becoming more organized or sometimes fluctuating depending on local conditions. These changes matter because magnetic field orientation influences how the solar wind interacts with planetary magnetic fields, even without sudden eruptions from the Sun. These steady interaction regions can carry significant energy and momentum through space. The boundaries of the region evolve as it travels. Close to the Sun, the compression may be moderate, but farther out, the accumulated effect of continued interaction can sharpen the structure. In some cases, a forward shock forms ahead of the compressed zone, and a reverse shock forms behind it, marking transitions between different flow regimes. These shocks are observed by spacecraft as sudden changes in particle speed, density, and magnetic field. They demonstrate that the solar wind is not a simple, smooth flow, but a dynamic medium where different streams interact and reshape each other over vast distances. The recurrence of these structures is a notable feature. If a coronal hole remains stable over several rotations, the resulting fast stream and its associated interaction region can appear again and again in near-Earth space. Observations indicate that such recurrent patterns can influence conditions around Earth over extended periods. The timing of their arrival becomes predictable to some extent, based on the rotation of the Sun and the persistence of the source region. This predictability contrasts with more sudden solar events, which can occur with less warning. The steady nature of coronal hole outflow allows for longer-term monitoring and forecasting. As the interaction region travels outward, it also carries fluctuations in plasma and magnetic field that originate both from the Sun and from the interaction process itself. Turbulence can develop within the compressed zone, adding complexity to the flow. Despite this, the overall structure remains recognizable as a region of enhanced density and magnetic strength between faster and slower streams. This combination of order and variability characterizes much of interplanetary space. It is neither completely uniform nor entirely chaotic. Instead, it contains patterns that can be followed over time, even as smaller details shift continuously. For Earth, the importance of these regions lies not only in their presence, but in their timing and structure when they arrive. The planet's orbit brings it into the path of these spiraling streams at intervals determined by solar rotation and the relative positions of source regions. When a co-rotating interaction region reaches Earth's vicinity, it alters the local solar wind conditions. The increased density and magnetic field strength can enhance the transfer of energy into Earth's magnetic environment, especially if the magnetic field carried by the wind aligns in certain ways with Earth's own field. In this outer to inner progression, the fast solar wind from a coronal hole has now become part of a larger interplanetary structure. It is no longer only a stream leaving the Sun. It is a moving region shaped by interaction with slower flows, carrying compressed plasma and magnetic fields across space. This structure bridges the gap between solar atmosphere and planetary environment. It shows how a feature that begins as a dark region in the corona can develop into a broad, traveling disturbance in the heliosphere. The journey from Sun to Earth is not empty or silent. It is filled with motion, interaction, and gradual transformation. The fast wind expands, meets resistance, compresses, and forms organized regions that persist across millions of kilometers. These regions carry the imprint of their solar origin while adapting to the conditions of interplanetary space. By the time they approach Earth, they have become part of a larger pattern of solar influence, linking the outer atmosphere of the Sun to the immediate surroundings of a planet through a continuous chain of physical processes. As the compressed regions and fast solar wind approach Earth, they encounter a boundary that belongs to the planet rather than to the Sun. This boundary is the magnetosphere, a region of space dominated by Earth's magnetic field. The magnetosphere forms because Earth generates a magnetic field deep within its interior, where motion in the liquid outer core creates electric currents. These currents give rise to a global magnetic structure that extends far into space, surrounding the planet and interacting with the solar wind that flows past it. The magnetosphere is not fixed in shape. It responds continuously to the pressure of the incoming solar wind. On the side facing the Sun, the field is compressed into a rounded boundary at a distance of several tens of thousands of kilometers from Earth. On the opposite side, away from the Sun, the magnetic field stretches into a long tail that extends far into space. This asymmetry reflects the balance between Earth's internal magnetic pressure and the external pressure exerted by the solar wind. When the solar wind becomes stronger or faster, the dayside boundary is pushed closer to Earth. When the wind weakens, the magnetosphere can expand outward again. The outermost boundary of this region is called the magnetopause. It marks the place where the pressure of the solar wind is balanced by the magnetic pressure of Earth's field. Beyond this boundary lies the solar wind itself, flowing past the planet. Just outside the magnetopause, the solar wind is slowed and heated in a region called the bow shock. A bow shock forms when a supersonic flow encounters an obstacle. In this case, Earth's magnetic field. The flow cannot adjust smoothly, so it transitions abruptly, changing speed, density, and temperature. This region of altered flow then continues around the magnetosphere, forming a sheath of turbulent plasma that surrounds the magnetic boundary. Inside the magnetosphere, conditions are very different from those in the solar wind. The plasma is less dense, and the motion of particles is guided primarily by Earth's magnetic field. Charged particles spiral along magnetic field lines, moving between the northern and southern polar regions. Some of these particles are trapped for long periods, forming regions known as the radiation belts. These belts contain energetic electrons and ions that circle the planet, held in place by the magnetic field. Their intensity and structure can change when the magnetosphere is disturbed by incoming solar wind conditions. The interaction between the solar wind and the magnetosphere is governed largely by magnetic fields. When the magnetic field carried by the solar wind meets Earth's field, the two can connect through a process known as magnetic reconnection. Reconnection occurs when oppositely directed magnetic field lines break and reconnect in a new configuration, allowing energy and plasma to transfer across the boundary. This process can open a pathway for solar wind energy to enter the magnetosphere, especially when the interplanetary magnetic field points in a direction opposite to Earth's field at the boundary. Observations indicate that such alignment enhances the coupling between the solar wind and the magnetosphere, leading to stronger disturbances within the system. When a co-rotating interaction region or a fast solar wind stream arrives, the increased pressure and magnetic field strength can intensify this interaction. The magnetosphere may compress more than usual, and reconnection rates can increase. Energy transferred into the magnetosphere is then stored in its magnetic field, particularly in the stretched tail region on the night side. Over time, this stored energy can be released, driving motion of plasma within the magnetosphere and sending particles toward Earth's upper atmosphere. These processes form part of what is known as geomagnetic activity, a measure of how disturbed Earth's magnetic environment becomes under solar influence. The magnetosphere acts as a protective shield in a broad sense. It deflects much of the solar wind around the planet, preventing the direct impact of high-speed plasma on the atmosphere at most locations. Without this magnetic barrier, the solar wind could interact more directly with the upper atmosphere, potentially leading to gradual loss of atmospheric particles over long periods. The presence of the magnetosphere therefore contributes to the long-term stability of Earth's atmosphere. However, the shield is not complete or impermeable. Under certain conditions, especially during strong solar wind interactions, energy and particles can enter and circulate within the magnetosphere, producing visible and measurable effects. The structure of the magnetosphere includes several distinct regions. On the day side, the compressed field forms a boundary that shifts in response to solar wind conditions in the magnetotail. The stretched field lines form a central sheet where plasma can accumulate and move. Closer to Earth, the inner magnetosphere contains the radiation belts and the plasmasphere, a region of relatively dense, cold plasma co-rotating with the planet. Each of these regions responds differently to changes in the solar wind, but all are connected through the overarching magnetic field structure. Measurements from spacecraft have mapped these regions in detail. Satellites orbiting Earth at various distances provide data on particle populations, magnetic field strength, and electric fields. These observations show that the magnetosphere is dynamic, with boundaries that move, currents that flow, and regions that change in response to external forcing. Even during relatively calm solar conditions, the system exhibits motion and variation. When disturbed by fast solar wind streams or interaction regions, these changes become more pronounced. The arrival of a high-speed stream from a coronal hole does not necessarily produce the most intense geomagnetic storms, but it often leads to sustained periods of moderate activity. The compressed plasma and enhanced magnetic field carried by the stream interact with Earth's field over hours or days, maintaining a level of energy input that can keep the magnetosphere in an active state. This sustained interaction distinguishes it from brief, more intense events associated with sudden solar eruptions. The magnetosphere responds not only to the strength of the incoming flow, but also to its duration and magnetic orientation. In this inward progression, the focus shifts from the solar atmosphere and interplanetary space to Earth's own magnetic environment. The magnetosphere stands as the interface where solar influence meets planetary protection. It shapes how energy from the sun is absorbed, redirected, or stored. It determines the pathways along which particles move and the conditions under which they can affect the atmosphere below. The steady arrival of solar wind, whether slow or fast, finds its consequence here, at the boundary where a planet's magnetic field stands against a continuous stream from its star. Below the magnetosphere, Earth's upper atmosphere forms the next region in the chain of solar influence. This is not the lower air of weather, cloud, and rain. It is a much thinner realm where the atmosphere gradually blends into near-Earth space. In these high layers, sunlight breaks apart atoms and molecules, creating charged particles and producing the ionosphere. The ionosphere is the part of the upper atmosphere where gas becomes ionized by solar radiation. It extends across broad heights and varies with day, night, season, latitude, and solar activity. Under quiet conditions, it already plays an important role in radio communication and in the electrical environment surrounding Earth. Under disturbed conditions, it becomes more dynamic, responding to both energy arriving from above and electric currents flowing along magnetic pathways. The upper atmosphere includes the thermosphere, where temperature increases with height because sparse gases absorb energetic solar radiation. Temperature here does not mean warmth as it is felt near the ground. The gas is so thin that even when particle energies are high, total heat content remains low. Still, these energetic particles and radiation alter the structure of the atmosphere. They change its density, chemical balance, and electrical state. When the solar wind and magnetosphere remain quiet, these changes follow fairly regular patterns tied to sunlight. During intervals of geomagnetic activity, the pattern becomes more disturbed. Energy deposited from above can heat the thermosphere, expand it outward, and drive winds that move around the planet. At high latitudes, near the magnetic poles, the connection between space and atmosphere becomes especially direct. Earth's magnetic field lines dip downward there, guiding charged particles from the magnetosphere into the upper atmosphere. These regions are known as auroral zones because they are where auroras most often occur. An aurora forms when energetic particles, mainly electrons and sometimes ions, enter the upper atmosphere and collide with atoms and molecules of oxygen and nitrogen. These collisions transfer energy to the atmospheric particles. When that energy is later released as light, the sky glows in moving curtains, arcs, or diffuse patches. The process is physical and specific. It is not simply coloured air, but light emitted by excited atoms and molecules returning to lower energy states. The colour of the aurora depends on which particles are emitting light and at what altitude the emission occurs. Oxygen can produce green light in one common transition and red light in another, while nitrogen contributes blue and red-purple tones under some conditions. The exact appearance depends on altitude, particle energy, and atmospheric composition. Because the upper atmosphere is thin, the path of incoming particles matters. Magnetic field lines guide them downward, so auroral forms often trace the geometry of those invisible lines. What appears from the ground as a quiet arch or a moving curtain is part of a much larger electromagnetic process linking the magnetosphere and the atmosphere. During the arrival of a fast solar wind stream or a co-rotating interaction region, the magnetosphere often enters a more active state. Electric currents strengthen. Magnetic energy is transferred more efficiently, and more particles can be accelerated along field lines toward the poles. The auroral zones may brighten and expand toward lower latitudes. The ionosphere becomes more disturbed, with changing currents and irregular distributions of charged particles. These changes do not remain confined to light in the sky. They alter the behavior of radio waves passing through the ionosphere and can affect systems that rely on stable signal propagation. The upper atmosphere also responds through heating and expansion. When geomagnetic energy is deposited there, neutral gases in the thermosphere gain energy through collisions with charged particles and through current-driven processes. The atmosphere swells outward slightly, increasing density at heights where many satellites orbit. This change is usually small in everyday terms, but it matters in orbital mechanics. Increased atmospheric drag can slowly lower satellite orbits and complicate tracking. The effect is strongest for spacecraft in low Earth orbit, where even thin atmospheric changes influence motion over time. The auroral zones are not narrow fixed circles painted on the planet. They shift with geomagnetic conditions. During quiet times, they tend to remain closer to high latitudes. During stronger disturbances, they expand, bringing auroral light to regions farther from the poles. This expansion reflects changes in the magnetosphere and in the currents that link it to the atmosphere. Observations from ground stations, aircraft, and satellites show that auroras can brighten, pulsate, drift, or break into moving structures across minutes and hours. These motions reflect variations in particle precipitation, electric fields, and magnetic reconnection in Earth's space environment. The ionosphere, though invisible to ordinary sight, is equally important. It contains layers of enhanced electron density created mainly by solar ultraviolet radiation. These layers refract, reflect, or absorb radio waves depending on frequency and atmospheric state. During geomagnetic disturbances, the density structure can become irregular, patches, gradients, and turbulent variations may appear, especially in polar and equatorial regions. Such irregularities can scatter radio signals and degrade satellite navigation accuracy. The upper atmosphere therefore serves not only as a luminous screen for auroras, but also as an electrically active medium through which much of modern communication must pass. In this region, Earth's atmosphere no longer behaves as an isolated planetary shell. It becomes part of a coupled system extending upward into space. Solar radiation from the Sun sets the baseline state of ionization. Magnetospheric energy, driven by solar-wind interaction, adds variability from above. Neutral winds, chemistry, and global circulation spread the effects horizontally and vertically. The result is a layered response in which light, electricity, motion, and composition all change together. The upper atmosphere is therefore not merely acted upon. It also helps shape the final expression of space weather at the edge of the breathable world below. Seen from this inward path, the auroral zone marks a natural place where solar influence becomes visible to human eyes. A coronal hole on the Sun leads to far solar wind. The far stream shapes interaction regions in space. Those regions disturb the magnetosphere, and the magnetosphere channels energy into the high atmosphere. Here, however, the process remains within the atmospheric response itself. The focus is on the thin gases above Earth, below the magnetosphere, yet still far above the weather and clouds of the lower atmosphere, lies the region where solar-driven energy begins to leave a visible and physical mark on Earth's air. This is the upper atmosphere, including the thermosphere and ionosphere. The thermosphere is a high layer where temperature rises with altitude because the thin gas absorbs energetic radiation from the Sun. The ionosphere is the part of the upper atmosphere where sunlight and particle impacts remove electrons from atoms and molecules, creating a mixture of neutral gas and charged particles. These layers are not separate in a sharp way. They overlap and interact, forming a broad transition between the denser air below and the space environment above. The upper atmosphere is already shaped by the Sun even during quiet times. Ultraviolet light and X-rays from the Sun ionize the gas during the day, creating layers of charged particles that affect radio waves and electrical behavior. The amount of ionization changes between day and night, with latitude, and across the solar cycle. In this sense, Earth's upper air is always part of the solar environment. It is not isolated from space. It responds directly to radiation from the Sun, and indirectly to energy entering through the magnetosphere. During periods of enhanced solar-wind interaction, that response becomes stronger and more structured. One of the clearest expressions of this response appears in the auroral zones. These are ring-shaped regions around the magnetic poles where auroras occur most often. An aurora is light emitted by atoms and molecules in the upper atmosphere after they are excited by energetic particles. Excited means that the particles in the gas have absorbed energy and moved into higher energy states. When they return to lower states, they release that energy as light. In Earth's upper atmosphere, the main gases involved are oxygen and nitrogen. Their emissions create the familiar green, red, blue, and violet colors seen in auroral displays, though green is the most common in many observations. The particles that produce auroras do not usually come straight down from the sun in a simple direct line. Instead, many are guided through Earth's magnetosphere and accelerated along magnetic field lines into the upper atmosphere near the polar regions. The auroral zones exist because Earth's magnetic field channels charged particles toward these high latitudes. When energy from the solar wind enters the magnetosphere, part of it eventually drives electric currents and particle motion that send electrons, and sometimes ions, downward into the upper atmosphere. As these particles collide with atmospheric gases, they transfer energy and produce light. Different colors arise from different gases and from different heights. Green auroral light often comes from oxygen at altitudes around 100 kilometers or more, while red light can come from oxygen higher up where collisions are less frequent. Blue and violet tones are commonly associated with nitrogen and molecular nitrogen. The exact appearance depends on particle energy, altitude, and atmospheric composition at the time. Thin curtains, arcs, rays, and diffuse glows can all occur. These forms reflect the structure of Earth's magnetic field and the changing electric currents in near-Earth space, rather than any simple wind pattern in the ordinary atmosphere. When a fast solar wind stream from a coronal hole reaches Earth and drives sustained geomagnetic activity, auroras often become more frequent and can expand farther from the poles than usual. The process is not instantaneous. Energy first enters the magnetosphere, circulates through magnetic and electric pathways, and then is released into the upper atmosphere. Over hours, the auroral oval, the ring-like zone of typical auroral activity, can brighten, broaden, and shift. Observations show that recurrent high-speed streams often produce repeated nights of enhanced auroral display, especially when the interplanetary magnetic field remains favorably oriented for energy transfer into Earth's magnetic system. The upper atmosphere responds in other ways as well. Heating increases in the thermosphere during geomagnetic disturbance. This heating causes the gas to expand upward, changing the density at altitudes where many satellites orbit. Even a small density increase in such thin air can matter for spacecraft over time, increasing drag and gradually altering orbits. In the ionosphere, changes in the electron density can affect how radio waves travel. Signals may reflect differently, scatter more strongly, or become less reliable in certain frequency ranges. Navigation systems that depend on signals passing through the ionosphere can also be affected because the speed and path of those signals depend on the charged environment they cross. Electric currents intensify in the upper atmosphere during geomagnetic activity. Some of these currents flow horizontally through the auroral regions, linking the magnetosphere and ionosphere into one connected system. The moving charged particles and currents can alter magnetic conditions at Earth's surface, which is why geomagnetic observatories detect storms even far below the visible aurora. The upper atmosphere is therefore not only a passive screen on which light appears, it is an active electrical region where energy from space is deposited, transformed, and redistributed. Despite this activity, the upper atmosphere remains extremely thin compared with the air at ground level. A person standing beneath an aurora sees luminous forms spread across the sky, but the emitting gas lies at heights far above aircraft and weather. The light appears near and immediate, yet its source belongs to a rarefied realm where particles travel long distances between collisions. This thinness helps explain why auroras can glow with delicate structure, rather than with the diffuse blur expected in denser air. It also explains why the same region can be highly responsive to relatively small changes in incoming energy. The auroral zones, then, represent a meeting place between planetary atmosphere and space plasma. They are fixed neither by geography alone nor by weather alone, They are organized by magnetism, the solar wind, after leaving the Sun, crossing the heliosphere, interacting with Earth's magnetosphere, and transferring energy through reconnection and currents, finds one of its most visible outcomes here. Light appears in the upper atmosphere because energy carried from the Sun ultimately reaches atmospheric gases and alters their atomic states. The path is long, but the result is direct. In this inward sequence, Earth's magnetic shield has now given way to Earth's upper air. The boundary response has become atmospheric consequence. The magnetosphere stores and channels energy, while the thermosphere and ionosphere receive part of that energy in forms that can be seen, measured, and felt indirectly through technological effects. Auroras are the most graceful sign of this exchange, but they are not the only one. The upper atmosphere as a whole becomes more active under sustained solar forcing, changing in brightness, density, ionization, and electrical behavior. It is here, above the weather and below the broader magnetic cavity, that the Sun's influence takes luminous form in Earth's own sky. When sustained solar wind from a coronal hole reaches Earth and drives geomagnetic activity, the effects do not remain confined to the upper atmosphere and polar sky. They extend into the technical systems that surround modern life. Many of these systems operate in regions directly exposed to space conditions or depend on signals that pass through the upper atmosphere. For that reason, a moderate but long-lasting geomagnetic disturbance can matter even when nothing dramatic is visible at ground level outside the auroral zones. The effect is usually not one of sudden destruction. More often it is a matter of altered conditions, increased stress, reduced accuracy, temporary interruption, or gradual wear placed on devices and networks that normally function within a narrower range of space weather conditions. Satellites are among the first systems to feel this stress. Many orbit within or near the upper reaches of the atmosphere and within Earth's magnetosphere, where changes in plasma density, energetic particles, and atmospheric drag can alter their operating environment. During geomagnetic activity, the thermosphere heats and expands. This causes the very thin air at orbital heights to become denser than usual. A satellite moving through that denser gas experiences greater drag, which slowly lowers its orbit unless corrected. Low Earth orbit spacecraft are especially sensitive to this effect. The change may be small over hours, yet over days it can become operationally important, requiring orbit adjustment and more careful tracking. Energetic particles also matter. Satellites contain electronics that can be disturbed when high-energy particles penetrate shielding or accumulate charge on surfaces and internal materials. Surface charging and internal charging can lead to discharges, brief electrical events that disrupt normal behavior. A spacecraft may experience temporary anomalies, sensor noise, false commands, or interruptions in communication. Most well-designed satellites are built with these risks in mind, but the risk increases during active space weather. Solar wind streams from coronal holes often produce recurrent periods of elevated energetic electrons in parts of the magnetosphere, and these electrons can be particularly troublesome for satellites in geostationary orbit and other high-altitude regimes. Radio communication can also be affected. Some radio systems rely on the ionosphere to reflect signals over long distances. Others pass signals through the ionosphere on their way between satellites and receivers on the ground. In both cases, changes in electron density matter. During geomagnetic disturbance, the ionosphere becomes less stable and more structured. Regions of enhanced or depleted ionization can appear, drift, and break up. These changes can cause fading, delay, scattering, and loss of coherence in radio signals, high-frequency radio communication, which is important for aviation, maritime use, and some remote operations, can become unreliable. The severity depends on latitude, time of day, season, and the detailed state of the ionosphere at that moment. Navigation systems are especially sensitive to ionospheric change because they depend on precise timing of radio signals traveling from satellites to receivers. A signal moving through a variable ionosphere does not travel exactly as it would through empty space. The delay introduced by charged particles can usually be estimated and corrected, but during disturbed conditions the ionosphere becomes more irregular. Rapid small-scale changes can reduce positional accuracy. In some cases, the signal may scintillate, meaning it fluctuates quickly in amplitude and phase. Scintillation can make it harder for receivers to maintain lock on navigation satellites, especially at high and equatorial latitudes where ionospheric irregularities can be pronounced. The result may be degraded positioning, timing error, or temporary service interruption. Power systems on the ground can also respond to geomagnetic storms. The connection may seem indirect, since electrical grids sit far below the magnetosphere and upper atmosphere. Yet changing magnetic fields above Earth can induce electric fields at the surface. Induction is the generation of electric currents by changing magnetic conditions. In long conductors such as power transmission lines, pipelines, and undersea cables, these induced fields can drive unwanted currents. In power grids, geomagnetically induced currents can flow through transformers and other equipment, causing extra heating, inefficiency, protective trips, or in rare severe cases physical damage. High-latitude regions are often more exposed because geomagnetic variations are stronger there, but effects can extend to lower latitudes during larger disturbances. The disturbances associated with coronal hole streams are often less extreme than those produced by the most powerful coronal mass ejections, but they can last longer and recur over several solar rotations. This persistence matters operationally. A brief intense storm presents one kind of challenge. Repeated and moderate activity presents another. Satellite operators may need to manage charging risk for many days. Grid operators may need to watch transformer behavior over extended intervals. Aviation routes over polar regions may face repeated communication concerns. The burden comes not only from peak intensity, but also from duration and repetition. Human activity in space is affected as well. Astronauts in low Earth orbit are partly shielded by Earth's magnetic field and by the spacecraft structure, but changes in radiation environment still matter for mission planning and monitoring. Spacewalks, spacecraft orientation, communication schedules, and instrument exposure may all be reviewed carefully during active periods. The same attention applies to robotic missions. Spacecraft that observe Earth, relay communications, or provide navigation all depend on predictable conditions for best performance, and space weather reduces that predictability. There are also subtler technological effects. Surveying systems that require precise positioning can lose accuracy. Timing networks that support finance, telecommunications, and distributed infrastructure can experience small but meaningful errors if navigation signals degrade. Radar performance can change in some frequency bands. Even satellite imagery can be affected if sensor calibration or orbital position shifts under disturbed conditions. None of these outcomes is automatic in every event, and many systems are designed with resilience. Still, the pattern is clear. Modern infrastructure extends into and depends upon regions of near-Earth space that remain physically connected to the Sun. Observations indicate that recurrent high-speed streams from coronal holes are a major source of moderate geomagnetic activity during some phases of the solar cycle. Because these streams can be tracked as the sun rotates, they are often forecast with some warning. This improves preparedness, but forecasting does not remove vulnerability. The exact effect on a given system depends on many local details, including equipment design, geographic location, orbital altitude, magnetic orientation of the incoming wind, and the state of the atmosphere and magnetosphere before the disturbance arrives. What can be said with confidence is that solar-driven changes in near-Earth space have practical consequences for technological systems, and coronal holes are one regular source of such change. Thus the path from the sun reaches into machines as well as skies. A darker region in the corona, defined by open magnetic fields, gives rise to fast solar wind. That wind interacts with slower flows, forms compressed regions, strikes Earth's magnetosphere, alters the upper atmosphere, and finally places stress on satellites, signals, and electrical networks. The chain remains physical at every step. Technology does not sit outside nature. It operates within planetary and solar conditions. And those conditions vary. During active intervals, the quiet functioning of orbit, communication, navigation, and power depends on how well human systems endure the changing influence of a star. To understand and anticipate the effects of a coronal hole on Earth, observation must begin at the Sun and continue across the space between star and planet. This work is called space weather monitoring and forecasting. Space weather refers to changing conditions in the Sun, the solar wind, Earth's magnetosphere, and the upper atmosphere that can affect technology and, at times, human activity. Forecasting these conditions is not a matter of simple visual inspection. It depends on a chain of measurements, models, and repeated comparison between what is seen at the Sun and what later arrives near Earth. The aim is not absolute certainty. It is to estimate the timing, structure, and likely effect of solar influences with enough accuracy to support scientific understanding and practical preparation. Observation of coronal holes begins with solar imaging. Spacecraft equipped with instruments sensitive to ultraviolet and extreme ultraviolet light reveal the hot corona in detail. In these images, coronal holes appear darker because the plasma there is less dense and often cooler than in surrounding bright regions. Repeated images taken over hours and days allow scientists to trace the size, shape, and position of each hole as the sun rotates. A hole near the center of the solar disk is often more relevant for Earth than one near the edge, because plasma flowing outward from a central region is more likely to be directed along a path that intersects Earth's orbit. The width and persistence of the dark region also matter. A broad, long-lived hole can produce a long interval of high-speed solar wind. Magnetic measurements at the Sun provide another essential layer of information. Instruments map the magnetic field at the photosphere, showing where positive and negative polarity dominate. These maps help identify open field regions associated with coronal holes and support models that estimate how solar magnetic structure extends into the corona and heliosphere. Since coronal holes are fundamentally magnetic features, imaging alone is not enough. A dark coronal region gains meaning when combined with magnetic context. Observations indicate that large areas dominated by one polarity are often linked to open magnetic flux, and therefore to fast solar wind outflow. From these measurements, forecasting centers build models of the solar corona and solar wind. Some models attempt to reconstruct the large-scale magnetic field above the Sun. Others simulate the flow of solar wind outward through interplanetary space. The goal is to estimate not only whether a high-speed stream will form, but also when it will arrive at Earth, how long it will last, and how strong the magnetic and plasma conditions may be. This task remains challenging. The sun rotates. Source regions evolve, and the solar wind does not travel through a fixed or uniform medium. Interaction with slower wind can strengthen or alter the stream along the way. Forecasting, therefore, involves both physics and uncertainty management. Spacecraft positioned between the Sun and Earth provide a second crucial stage of monitoring. Some are placed near the first Sun-Earth Lagrange point, a location where the combined gravitational pull of Earth and Sun allows a spacecraft to remain in a relatively stable position, roughly 1.5 million kilometers sunward of Earth. From there, instruments can sample the solar wind before it reaches Earth. They measure speed, density, temperature, and magnetic field direction in real time. These measurements do not provide many days of warning, but they do provide valuable notice, often on the scale of tens of minutes to about an hour, depending on solar wind speed. This near real-time monitoring is especially important because the magnetic orientation of the arriving plasma strongly influences geomagnetic response, and that orientation is difficult to determine reliably from solar images alone. Forecasting agencies combine these layers of information. Solar images identify potential source regions. Magnetic maps and models estimate whether the field is open and whether a coronal hole is likely to produce Earth-directed fast wind. In situ measurements near the Sun-Earth line then confirm what is actually arriving. Ground-based magnetometers, ionospheric instruments, and auroral observations track how Earth responds once the solar wind reaches the magnetosphere. The full forecasting chain therefore runs from solar atmosphere to near-Earth space, and then into the atmosphere and surface environment. Each stage corrects and refines the interpretation of the others. Coronal holes are among the more forecastable solar features because they can persist for multiple solar rotations. When a long-lived hole reappears after the Sun turns, forecasters can compare present conditions with what occurred during earlier passages. This recurrence improves confidence in broad timing. If a similar hole produced a high-speed stream about 27 days earlier, a renewed stream may be expected again after the next rotation, provided the hole remains intact. Even so, the comparison is never exact. The shape of the hole may change, the surrounding slow wind may differ, and the magnetic field within the arriving stream may not match the earlier event. Forecasts, therefore, often express likelihood and expected range rather than exact outcome. Ground-based observatories remain important despite the central role of spacecraft. Solar telescopes on Earth monitor the Sun in visible and some other wavelengths. Radio observatories detect solar emissions linked to activity in the corona and heliosphere. Networks of magnetometers measure disturbances in Earth's magnetic field across different latitudes. Ionosondes and receivers that monitor navigation signal delay provide information about the state of the ionosphere. All of these observations help assess the effects of incoming solar wind and verify whether forecasts capture the actual behavior of the Earth system. Monitoring is therefore not only a matter of watching the Sun, it is also a matter of watching Earth respond. Forecast products often describe expected solar wind speed, geomagnetic conditions, auroral probability, and possible technological impacts. These products are used by satellite operators, electric grid managers, aviation planners, scientific teams, and others whose work depends on near-Earth space conditions. The language of forecasting tends to be probabilistic because the system is too complex for perfect certainty. A coronal hole can be identified clearly, and a fast stream may be highly likely. Yet the exact strength of geomagnetic response still depends on the magnetic field orientation within the stream and on the pre-existing state of Earth's magnetosphere. This is one of the central limits of current forecasting. Even with those limits, observation has advanced greatly. Modern instruments allow scientists to watch the corona continuously, sample the solar wind directly, and compare predictions with outcomes across many events. The result is a steadily improving ability to connect solar source regions with effects at Earth. Coronal holes, once visible only during eclipses in the broad corona, are now tracked as dynamic features with known consequences for heliospheric flow. Their recurrence, size, and magnetic character make them a major part of operational space weather science. In this stage of the inward path, attention rests on the act of watching itself. The Sun is observed not as a distant symbol, but as a measurable physical system. Dark regions in the corona are mapped, magnetic structure is inferred, solar wind is sampled in transit, and Earth's response is recorded in fields, particles, and atmospheric change. Forecasting does not remove uncertainty, but it turns a remote solar feature into a monitored cause with estimated terrestrial consequence. Through this work, the connection between a coronal hole and Earth becomes not only a scientific chain of processes, but also a practical chain of measurement, interpretation, and warning. At this point in the path from outer space to Earth, the broad chain of processes is visible in full. A coronal hole appears in the Sun's outer atmosphere as a region of reduced density and lower emission in ultraviolet and X-ray light. Its underlying cause is magnetic structure. Field lines in that region are more open than in the bright loop systems nearby, allowing hot plasma to flow outward more easily into interplanetary space. This part of the picture is well established through repeated observation from solar spacecraft, through magnetic measurements of the photosphere, and through the direct sampling of the solar wind far from the Sun. The so-called massive hole is therefore real as a coronal feature, but its reality belongs to atmospheric structure and magnetic openness, rather than to any literal gap in the star. From such a region, fast solar wind emerges. This, too, is securely known. Spacecraft measure recurring high-speed streams and identify their origin in long-lived coronal holes seen rotating across the Sun. The connection is one of the strongest in solar terrestrial science. When the source region persists for more than one solar rotation, the resulting stream may return at roughly regular intervals, allowing forecasters to anticipate another period of enhanced solar wind when the hole again faces Earth. The broad timing of this recurrence is often reliable. It rests on the rotation of the Sun, the persistence of the coronal hole, and the measured travel time of the stream through the inner heliosphere. It is also well known that these high-speed streams interact with slower solar wind ahead of them. The result is a compressed region in interplanetary space, where density and magnetic field strength increase. By the time this disturbed flow reaches Earth, it may be capable of driving geomagnetic activity for many hours or even days. Observations from spacecraft near the Sun-Earth line repeatedly confirm the arrival of such streams and their associated compressed regions. Ground-based magnetometers and upper atmosphere measurements then confirm Earth's response. Auroras intensify, the thermosphere expands, ionospheric conditions change, and magnetospheric currents strengthen. Satellites, communication systems, navigation signals, and power infrastructure may all experience measurable effects. The physical chain from coronal hole to terrestrial consequence is therefore strongly supported by evidence. What remains uncertain is not whether this chain exists, but how strong any given event will become and exactly how Earth will respond. Much of that uncertainty centers on magnetic orientation. The solar wind carries an embedded magnetic field, and Earth's magnetosphere responds most strongly when the arriving field points in a direction that favors magnetic reconnection at the dayside boundary. This directional detail is difficult to infer with high confidence several days in advance from solar images alone. A coronal hole can be clearly visible, and a fast stream can be expected. Yet the degree of geomagnetic disturbance still depends heavily on the magnetic structure within the arriving flow. That structure evolves as the stream travels outward and interacts with slower wind, making precise prediction difficult. There is also uncertainty in the detailed physics of coronal heating and solar wind acceleration. Observations indicate that magnetic waves, plasma expansion, and small-scale magnetic processes all contribute to the fast solar wind that emerges from coronal holes. However, the exact balance among these processes remains an area of active research. The broad framework is secure. Open magnetic fields permit escape, and wave-related and thermal processes help accelerate the outflow. Yet the full fine-scale mechanism, especially in the low corona where the wind is launched and gains speed, is not completely settled. This does not weaken the overall picture. It simply means that a mature scientific understanding can include both strong consensus and unresolved detail. Another uncertainty concerns how a coronal hole changes over time. Some holes remain stable across several rotations, while others distort, shrink, split, or merge with nearby open field regions. Their boundaries can be complex, and the surrounding coronal environment can influence the eventual shape and structure of the wind stream. A hole that looks large in one set of images may not produce the same near-Earth effect as a similar-looking hole seen weeks earlier. The difference may arise from changes in neighbouring magnetic regions, from variations in the background slow wind, or from altered structure within the stream itself. Appearance at the Sun is therefore highly informative, but not fully sufficient for exact terrestrial forecasting. The phrase solar storm also requires care. In public language, it is often used broadly for any period of increased solar influence on Earth. In scientific use, different solar drivers can produce different kinds of disturbance. Coronal holes commonly lead to recurrent high-speed streams and moderate geomagnetic storms, especially prolonged ones. The most severe geomagnetic storms are often associated instead with powerful coronal mass ejections, which are large expulsions of magnetized plasma from the solar corona. A coronal hole can still matter greatly, especially for satellites, auroras, and long-lasting geomagnetic unrest. But its typical effects differ from the effects of the most intense eruptive events. It is therefore accurate to say that a coronal hole can contribute to a solar storm affecting Earth, while also noting that not every coronal hole leads to extreme consequences. Forecasting has improved because the Sun is now observed continuously in multiple wavelengths, and the solar wind is sampled directly before it reaches Earth. Even so, the forecast remains a probability rather than a certainty. Agencies can identify a coronal hole, estimate when the fast stream may arrive, and warn of elevated geomagnetic risk. They can rarely specify every detail of strength, duration, and regional impact until the solar wind is much closer to Earth. This is a natural limit arising from a dynamic magnetic system stretched across millions of kilometers. Space weather prediction resembles weather forecasting. In this one respect, broad conditions can often be anticipated. While local and peak details remain less certain until the event unfolds, what is known, then, is substantial. Coronal holes are real features of the corona. They are regions of open magnetic field. They are major sources of fast solar wind. That wind can interact with slower wind, form compressed regions, reach Earth, and drive geomagnetic activity with visible and technological effects. What remains uncertain belongs mainly to the detailed strength, timing, and fine magnetic structure of any individual event. as well as to some of the deeper physical mechanisms by which the fast wind is heated and accelerated near its source. Scientific understanding in this field is neither vague nor complete. It is a strong framework with active frontiers. The inner end of the path therefore arrives at a balanced view. A large dark region on the Sun can indeed matter to Earth. It is not a myth, not a dramatic hole in the ordinary sense, and not a guarantee of catastrophe. It is a coronal region whose magnetic openness allows the Sun's outer atmosphere to flow outward more rapidly. If Earth lies in the path of the resulting stream, the planet may experience days of heightened geomagnetic activity, brighter auroras, disturbed upper atmospheric conditions, and added stress on technology that depends on quiet space. The science supports this connection clearly. The remaining uncertainty lies in the details, and those details are the work of continuing observation, modelling, and patient measurement. The planet continues its orbit beneath this steady exchange, above the familiar world of ocean, cloud, soil, and stone. A larger environment remains in motion. The Sun shines with visible calm, yet its outer atmosphere opens and closes along magnetic paths that no eye can see without instruments. From one of those open regions, thin plasma flows into space, crosses the dark between star and planet, and touches the boundary of Earth's magnetic field. The contact is gentle by human measure and immense by planetary measure. Light later appears in polar skies, signals shift, orbits alter by small degrees, currents move in wires and in the air above them. Nothing in this sequence needs exaggeration. The quiet truth is enough. Earth does not drift outside the Sun's reach. It lives within that reach, shielded in part, exposed in part, and continuously joined to its star by light, magnetism, and matter. A coronal hole is one expression of that connection, neither a wound nor a wonder beyond nature, but a recurring form in the life of an ordinary star. In the long movement from the edge of the heliosphere to the thin air above Earth, the same pattern remains. Space is not empty in the simple sense. The Sun is not still in the simple sense. Earth is not separate in the simple sense. Each remains part of one system, vast, quiet, and active at once, turning onward in measured relation.